Let's start in with the first one. So on our first one, the question is, where in the beam shown is the moment the highest? So Heather.
Great. So you can use intuition a little bit on this particular problem because as you can see by the dimensions of where the loads are located, that everything is symmetric about the beam. So by intuition, you can figure out what the reactions on each end are, and they are going to equal 3 kips apiece because I just took the 6 kips total that are applied to that beam and divided it in half because of everything being symmetric. Now, if you feel comfortable and you can go intuition-wise and keep going that way, you will ultimately come to the answer that the moment is highest right here at midspan. But for those of you that don't feel comfortable doing that way and want to do a little bit of the math behind it, we're going to show you how you can get there. So the thing that'll get us there is we're going to draw the shear diagram here for this beam where
I've always been curious why you use V for shear, but that's one of those engineer speak things.
So we're going to start by doing a shear diagram, and you're going to go up. You're going to follow your loads. So we're going to go up 3 kips, and because we don't have any load applied, we're going to go straight across, and then we're going to come down 2 kips. That's by my hand that does this. So we're going to come down 2 kips, and then we're going to go across again till we hit that next load, and we're going to come down 2 kips, which takes us across the 0 line and puts us at -1. And then we are going to go straight across, and then down 2 kips, straight across, and then close it up with that last 3 kips. Now, the one thing to know about your shear diagrams is whenever that shear diagram crosses 0, so this point right here, whenever that happens, that is your maximum moment.
So when that shear diagram crossed the 0 line, that we essentially have just answered the actual question right there. Like and it happens because this one is symmetrically loaded. It happens to be right in the middle, and you could have guessed that beforehand if you'd sort of been thinking about it. But this is sort of a clear description of why that's the case.
Correct. Yep. So if we move on to the next question,
well, why don't we go ahead and let's draw the moment diagram.
Okay, so let's do that. So
just for fun, because what could be more fun than drawing a moment diagram?
So yes, we are going to draw that moment diagram, and you need to know a couple of different things that I'll describe along the way. The first is to figure out what number you're going to go up to. We're going to do the area underneath this shear diagram. So we basically have a 3. We went up 3, so this value here is 3. And you're going to do the area of it. So it's 3 times 3, so it's 9. And whenever you have a straight across, so a box shape in your shear diagram, you're going to get a diagonal line in your moment diagram. So we're going to go up to 9, and then you're going to keep doing your math where you have, this is 1, and it's 6 feet long, so we're going to go up another 6 to the center. So we come up to 15.
So you were kind of doing those you're just kind of separating those out into different boxes. So the first one was the 3 kip amount by the first 3 feet, and then you jump to the next box, which was 6 feet long, but only 1 kip high.
Right.
And so you're kind of just adding it up as you go along.
Yep. And then because we crossed the 0 line, these are all negative, so we're basically going to come down those same numbers. So you're going to come down a total of 6 to the +9, and then you're going to come down the rest of the way down to 0.
So that just to be clear, that line probably shouldn't have been so straight looking, but there you go. And one of the ways to think about this that I find useful, not everybody finds useful, so if this confuses you, just forget about it, but that the slope of the line on the moment diagram is equal to the value of the shear diagram at that moment. So if you think about that, in that shear diagram up there, that first 3 feet, you have a value there, and there's a specific slope, and that's going to be a relatively steep slope. And then in that second box that we talked about for that next 6 feet, it's a lower number on the shear diagram, and so it's a lower slope. And this will become sort of more useful when you look at the next example. But this is one of those things where you start seeing there's this direct set of relationships, and you can do a whole series of calculations. We could have done this through sums of vertical and moment diagram, moment sums. But in fact, you can actually do this fairly quickly just by kind of graphically kind of playing it out.
Correct. Yep.
Why don't we go to the next one? So this is another very similar question, but this one's a little more complicated.
Yep. So intuition is only going to get me so far in this one because it's not symmetric, and I have two different load types. I've got a distributed load, and then I've got this concentrated load over here. So I need to figure out what my reactions are first to even attempt figuring out what my shear diagram is going to look like to figure out where my maximum moment is. So the way I like to do it is I'm going to sum about this left-hand side right here. And to do that, we're going to basically be summing a moment about that point. So to do that, we are going to look at the different direction the loads are going. So we are going to start out with the 1.5, and it is acting over 12 feet. And then you want to look at it and say, what's its moment arm? So its arm here basically is half of the distance it acts over. So it is another 12 over a half. So it's 6 feet.
So the first 1.5 times 12 is actually the total load that you're talking about.
Correct.
So the 12 foot is, because it's 1.5 kips per foot, in order to know what that total load of that particular one, you have to multiply it by the 12 feet. But then the moment arm is the half of that distance.
Correct. And so keep going with the next set of loads. So the 1.5 kip per foot is going to act in the same direction as that 4 kip load, and it is acting 15 feet away from this left end. And when we do this, all of this has to sum up to 0, because otherwise we don't have a static beam here. You don't want your beam galloping down the road.
Yes, flipping around.
Yeah. So I'm going to call this other end here B just to give us a value, but it is acting in the opposite direction that the other two loads are. So it's going to have a minus sign, and it is acting at, let's see, that's 6 and 12, that's 18 feet. And when you solve for B, it actually comes up to 9.33 kips. And then you can sum your forces in the vertical by saying this 4 kips plus the 1.5 times 12 to get it to a total load, and then subtracting off the 9.33 gets you to the reaction over here, which is 12.67. So when we draw our shear diagram here, we're going to start doing it the same way we did the other. So we're going to go straight up because we've got that 12.67 kip reaction, but we have a distributed load, so you got to treat that a little differently because every foot you're taking off more load. It's not like this concentrated load where it happens all at once. So because it's a distributed load, it actually is going to have, and I'm just going to draw some guidelines in here for myself because that's how I do things. So because of that, we're going to have this diagonal line that continually changes value every foot as you go, because you're going to subtract off that 1.5 kip every foot of the length of that 12-foot area that it acts across. So once you hit that, we see that there is no load then between the end of the distributed load and the concentrated load, but then you hit the concentrated load and it goes down a little bit more and then goes straight across and comes back up. So now we have seen that here's our point of maximum moment, because that's where it crosses 0. But we have to figure out what it is. And so there's a couple of different ways you can do it. I like to use similar triangles just because it's graphic for me, and that's what I like to do. So I have one triangle that I know it's 12.67 over some unknown value, but then my other triangle has to be the whole thing where it's the total of 12 feet down here, but then it's 12.67 plus the 5.33. I've done a little extra math for you here, but it's the sum of that. And then when you solve, you can basically then do your ratios and solve for x, and you get a value of x, which is 8.45 feet. That's how far away from this left end that point of 0 shear is.
And so that tells us our basic question, which was, where is the highest amount of moment?
Correct.
And we figured that out through a combination of using the shear diagram, understanding kind of what the shear diagram was telling us, and then doing a kind of a quick version of what kind of a fast graphic version of helping us understand where exactly that point of crossing is. But we also could have done a moment diagram. We could
could
have
have.
done a sum of moments and then figured out distances. Like there's a series of other things we could start to figure out as well.
Yeah, I guess the one thing that this helps you is, yes, you could have drawn that moment diagram, but if you're feeling crunched and frantic because of time, don't feel like you have to do that. By knowing that your point of zero shear is your maximum moment, you've saved yourself some time.
But just because we're narcissists like this, let's go ahead
right.
and show that, just to have a moment to discuss what these things look like.
Yep. So now, again, we have to think about that the point of moment is based on the area underneath this. So, and I haven't done this math, so I'm not going to really put values down, but I'm going to draw what the diagram looks like.
Yeah, so this is just sort of approximate.
Yep. So basically, because we have now a sloped line in our shear diagram, the line in the moment diagram needs to be a curve. So it's going to come up here and it's going to peak basically right there.
And we happen to know that because we've already figured that out.
Yep. So then it's going to start coming back down on a curve. Oop. Bad curve.
Bad curve, but a curve, okay.
Yep. So, but then when you hit this point where the diagonal stops, you've hit basically a constant slope line. So now you're going to get a straight line.
So a diagonal straight line, just like the previous one that we were doing.
Correct. Get one of those, and then you're going to get an even sharper one. It's difficult to tell from my very crude drawing.
Yeah, so not the greatest drawing on there, but there you go. And once again, the version that I was talking about, again, just find the system that you feel comfortable and how to think about these things. But if you think of it as that the value of the shear diagram is telling you what's going on the moment diagram, as that sloping line goes, the value is dropping at every point, and you can see that the curve, that's the slope is changing and becoming closer and closer to zero until it gets to that maximum point. So same kind of thing. So whatever system you find that helps you kind of see these things or be able to just think of them graphically, that's what you're looking for.